let's do this. So today is labeled as tree examples, and by default I'll just go through tree examples. I'll run the debugger in IntelliJ and just look at the structure of trees. But we have an opportunity to make this lecture more flexible, so I'll take questions and talk about the overall course, kind of like I did at the beginning of last lecture. If we do that for quite a while, hell, if we do that for the entire lecture, I'm fine with that too. I assume most of the class who's still working on genetic algorithm is probably most of the empty seats. So if what we have here is most of you being done with genetic algorithm, we have the opportunity to kind of talk about whatever interests you or whatever you want. If some of you or even most of you here are still working on genetic algorithm, I'd be happy to talk about that too. There's one question about GA that I'll talk about. I'll answer this one quick in the lecture channel. Oh, let's get this out of the way. Sup Dragos, Alex, Cole, what's going on? That working on AO1. So the first thing I want to say, I've been saying this to, I've said this early in the semester, I've said it a few times, and I've said it in like office hours and stuff, but I just wanted to mention it again in lecture so everybody's on the same page and everybody's aware of this. When the application objectives, when the deadlines are for those, because there's no deadline extensions for application objectives, but the actual deadline is a little undefined, it's a little loose is in terms of when you can still work on an application objective. Like technically, officially, it's tonight at 11:59, so technically it could shut off there, but I'm telling you it's not going to. So when AOs are kind of due, or when you can't get credit for them anymore, is like tomorrow, I'll kind of leisurely start my day, whatever I want to do that Saturday morning, wake up, drink my tea, whatever. And then by the time I get around to it, to sitting down with my laptop and looking at some work stuff, one of the first things I'm going to do is re-upload the grader with the application objectives shut off. So and when I do that, you'll get the feedback in Autolab, which above each application objective, it'll say, sorry, the checkpoint has passed. You can no longer earn credit for the application objective. So until you see that notice, which will probably be sometime tomorrow morning, it'll be tomorrow sometime tomorrow. Until you see that notice, that note, you can still earn credit for the application objectives. So once you see that, that means it's done. And officially, I can do that as early as the stroke of midnight. I'm telling you I'm not going to do that. I'm not going to enforce that. I leave myself the room in the schedule, the wording of everything to do that. But I keep it loose enough so I can give you more time. So I'll give you, you'll have more time. Don't stop at midnight if you're working on the application objectives. You can still get credit for them until you see that note in there. So I don't know exactly when I'm going to turn that off. I don't like having a strict deadline on that. If I see a lot of people are working on application objectives, I might drag my feet a little more on it and give you some more time. But until you see that note, you can still get credit for the application objectives. How in the past I actually forgot about it once and didn't change the grader until Monday, so technically you got the whole weekend to do that. It's not going to happen for this one. I'll change it tomorrow, but I just wanted to make sure that's clear because I reminded some students yesterday in office hours about that. I just want to make sure everybody has equal ground on that. Everybody's aware of that because I haven't mentioned it in lecture in quite a while. I didn't even answer the question. So I do leave the graders for feedback. When I do shut off the application objectives, it adds that note and you can't get credit for them anymore, but it will still give you the feedback. So the comment was, can I still get the feedback? The Autolab will still accept submissions for everybody 1 week past the checkpoint. So next Friday is when Autolab will shut off, and then if you get extensions after next Friday, select few students for certain circumstances can get more. Those will be individual. Not everybody will see those in Autolab. So until next Friday, you can still submit and get feedback on the application objectives. And even if you're working on AO2, the new feedback is going to say you don't have credit for AO1 anymore. If you got AO1 and working on AO2, you will still get that credit. When I process final grades at the end of the semester, as long as you have a submission with credit for an application objective, you have credit for that application objective. It's not only your latest submission. So even in the grade book, it'll show that you don't have credit for it. I will see that submission. I look for that stuff at the end of the semester, and you will get those application objectives that you rightfully completed. So you do still have an extra week anonymous. If that week isn't enough, let me know. I could If you have, well, obviously you'll have the right portion of the learning objective by then. I can give you, I can open it back up. I don't want to do it for everybody because a lot of students will see that deadline in Autolab and assume they have an extension. I've seen that way too much. But email me and I can give you an individual extension if you still want the feedback. Yes, Trey. Yeah, so is that what people want to talk about, AO1? I got 2 questions about AO1 already. I mean, I'd be happy talking about that. Does anybody want to talk about other stuff? Anybody want to see tree examples? This is a pretty flexible lecture. Whatever you want to see. I'll let you. You want to hear about application objective 1? You need it? Okay. I'm seeing confirmation, 3 confirmations right there. Let's talk about AO1. So, would the way to generate random animals be to take the length as number of genes and generate those lists? Yes. So to generate an animal, a random animal, to use the genetic algorithm terminology, you'll take the number of genes and then call math.random to generate your random values and create a random list of doubles with the length of that number of genes, and then take that list of doubles and throw it in an incubator function, and that's going to give you an animal based on those genes. A few things about this. The genes, if you just use math.random, your genes are all going to range from 0 to 1. It's not necessarily going to be the most effective genes. So you can take math.random, and like we were seeing in Wednesday's lecture, take math.random and scale and shift that range to your heart's content. A good range is, especially for my 2 hidden tests, is negative 100 to 100. If your genes are ranging from negative 100 to 100, you're going to cover a lot of solution space. I think I even give that hint in the document itself, if I'm not mistaken. That's a good range for your genes. So take math.random, minus 0.5, multiply by 200, you're going to get that range from that randomness. So don't feel restricted because math.random only gives you values 0 to 1. Scale that, shift the range, get whatever range you want out of math.random. Throw that in the incubator and you have an animal. One of the most effective parts of the genetic algorithm are the mutations. I've actually seen, I probably shouldn't say this, but it's the day of the deadline. I don't mind giving this hint. I have seen submissions in the past that don't do any crossovers, only do mutations and then add random animals. And they have really nice genetic algorithms, really optimal, really efficient. Gets to a fairly optimal solution very quickly with just mutations, if your mutations are nice. And so what do I mean by nice? What do I mean by that? Your mutations should take one list of genes. So you're taking one list of doubles of the appropriate length of the number of genes, and then mutate it by a little bit. I'll explain exactly what I mean by that. Mutate it a little bit, change those genes just a little bit so you have an animal that's very similar to that animal, but just a little bit different. The way I like to think of this is throwing darts at a dartboard. Your genetic algorithm, you're taking whatever your population size is, maybe you have 100 or 1,000 animals that you're generating each for the first generation anyway. You take all those darts and you just whip them at a dartboard randomly. Basically like you have a blindfold on, you spin around a few circles and just whip them all at the wall. And then you're going to take which ones, especially the one that's closest to the bullseye, with the goal of hitting the bullseye. Take the one that's closest to the bullseye, wherever that one landed, you want to search the area around that dart, whatever the best dart is. So in your code, what you're doing is generating a whole bunch of random animals, getting their costs, and finding the least cost animal. Once you have that least cost animal, when you create the mutations, you're searching the area around that best animal. So what you can do is take those genes, take that animal. First of all, that animal makes it to the next generation. No questions asked. That's your best animal. That's your best solution you've ever seen. That one goes to the next generation for sure. You also want to take that animal and generate several mutations of it, 5, 10, however many mutations you want, but a good number of mutations of that one. So take that animal and take each one of its genes and just randomly change it a little bit. If you pull out your math.random and you want a very little change here, pull out your math.random again, but now change that scale to something that's going to add a very small variation. So if you scale it down by maybe dividing it by 100, getting a scale from like negative 0.01 to positive 0.01 would be a good range. Get a random value in that range and add it to each one of the doubles in your gene. Send that to the next generation. Take your best animal again, create another mutation of it by adding randomness to it, send that to the next generation, generate a good handful of those, send them all to the next generation. So now you have your best animal, the dart that's closest to the bullseye, and a whole bunch of made-up darts that are very close to that area. Some of them are going to get closer to the bullseye, and some are going to get further away. The ones that get closer to the bullseye are going to be your best animals in the next generation, most likely. Maybe a random dart happened to get closer to the bullseye, and that's good too. But you're getting closer, trying to get closer to that bullseye with every generation. You do that for enough generations, you're going to be right in the center of that bullseye. So if you're struggling with your genetic algorithm, especially if you're failing my hidden tests, the first thing I like to look at is mutations. That's the first place I go in office hours when I have questions. Go to your mutations and make sure your mutations are giving you animals that are very close to that best animal. And you can create mutations of like your second and third best too, but your best animal, creating mutations of that is the most important step for each generation to be able to do that. Yes?
How many, I know you can't really give a true answer to this, but how many animals do you say we should start with? In the generic, steps you gave to make your genetic algorithm, you said take a fixed number of animals. How many do you
Enough, but not too many. 100 will work for you. A couple hundred. 100,000, just not too few that you're not going to get, like if you only throw 5 darts at that dartboard, maybe they all hit the wall. And not too many where your algorithm is so slow that it never converges. What I like to do is pick a fixed number of animals and a fixed number of generations, and then your recursion should be based on the number of generations. I see this mistake a lot. I don't know if anybody's still doing this, but your recursion should be based on your number of generations. So when number of generations remaining, or whatever you call your variable, equals 0, that's your base case, and your recursion always decrements that to run for a fixed number of generations. It's very dangerous to have your base case be anything. I shouldn't say anything else. There's probably some really, really cool way to do it. But for example, one trap students like to fall into, one thing I see in this assignment, is you check your best animal from the previous generation, its cost, check the cost of the best animal in this generation, and if the difference is 0, stop your recursion. Well, sometimes that's just going to happen by pure chance. You're not going to find the best animal, but you go to the next generation, one of your mutations or one of your random animals happens to be better. Don't leave that up to chance, that just because you had a generation that didn't happen to improve, it doesn't necessarily mean you're done. It doesn't necessarily mean you have a good solution. And the biggest trap, I think the way I restructured the assignment, I think I finally got rid of this one. Students would say, if cost equals 0, then end. Which of course causes infinite recursion. There's not always the best solution. There's, with the way the assignment is structured now, there's never a best song, like a song that's so good that it has 0 cost at all. You're never going to have a 0 cost. But I had students who would test with things where there always was a 0 cost solution, but then my tests, that wasn't true, and that caused some problems. I don't think anybody does that anymore with the way we're doing songs and playlists, though, because you catch that before you submit to AutoLab with this structure. You'll catch that in your own tests now. Enough is never enough. Yeah, 10,000. If you can have 10,000 animals, as long as it's efficient enough, as long as it's fast enough, it's whatever. But that's why there's that time limit. You can't just have a really crappy algorithm and just say 50,000 animals for 1,000,000 generations and let it run, and make sure you're setting up with tail recursion so you don't overflow the stack. Like, I don't want something like that where where you're defeating the point, where your algorithm takes minutes to converge. Is the map of YouTube IDs all for the same song? No, for LT5, the map of YouTube IDs, YouTube IDs to ratings are for different songs. So that's why it's a map. The keys in the map are YouTube IDs, and then the values are the ratings for that particular user. And the idea of that is a user has these current ratings. This is what they've liked in the past. This is what we know about this user. Let's throw that into our algorithm and figure out what they're going to most likely like in the future. Of course, we're not too sophisticated. We're just saying, well, if they don't like that song, then they probably don't like that song. We're not making any predictions based on that data, but that's where we would improve our models. We would take that map and then have some feature vectors for each song and say they liked these songs. Let's show them songs that are similar to the songs that they liked. That's where we would go with that, of course. It's only 116. There's only so much I can do without making the assignment ridiculous. And some of you would argue that it's already absurd. It's already too difficult. So I can't do too much with that. But that's where that idea is going. I just couldn't fit that all in the assignment, in a 116 assignment. If it was an AI course, a machine learning course, that's what that map would be used for. It would be used to have a more predictive model to be able to tell you, if you like those songs, you'll like these songs. Like what we see with the actual music apps or any, the algorithms that are out there. That's what those algorithms are doing. You like these in the past, you'll probably like this too. We just couldn't quite get there. Maybe someday. Maybe someday I'll be able to do that in a palatable way where it's not just too convoluted. I think that's just conversation happening in chat, right? No questions for me? And AO2, I mentioned this a few times, but AO2, if you're starting AO2 today, probably just cut your losses. That one's a beast. That is by far the most difficult application objective in the course. It's meant to be a real challenge. Don't start it today. Don't waste your time. I hate saying that. I don't like giving that advice for most things, but for this one, I'm sure you have a lot of other classes that are hitting you hard right now. Don't focus on those things instead of AO2 specifically. If you're starting AO1 today too, probably cut your losses. AO1's time-consuming. That one you probably could. Depends how dedicated you are. If you start AO1 right now, you probably could finish it with a lot of dedication and a pinch of luck. You could get there. AO2, no. AO2 starts with, at least an hour of studying what neural networks are before you can even start thinking about the question. Yeah. Than the previous homework twos? Is this AO1 harder than AO2, the loyalty sales AO2? It's hard to answer this because it really depends on what you're most comfortable with. I think all else being equal, I think this AO1 is more difficult than AO2 on the previous homework. I would say that's true. But in this case, since there's two very different things, it really depends on what you're most comfortable with. If you're more comfortable with OOP, then that AO2 would feel a lot easier. If you're more comfortable with FP, and all this first-order function stuff flying around, then AO1, and recursion, of course, then AO1 would be easier than AO2 on the previous homework. So they're close. I think AO2 on the previous one would be a little bit easier, all else being equal, but they're close. But it just depends on what you're most comfortable with. For example, if you did OOP in high school through the AP Computer Science, if you did that, then AO2 on the previous homework would probably be a lot easier because you already had a lot of background knowledge in classes and objects and inheritance and things like that. Whereas you probably didn't see recursion, first-order functions, or any of that. So I would say, in that case, that would be way easier. But if you saw functional programming, you're like, oh, that just makes a lot of sense, which I don't think many people do. That makes a lot of sense, then this one would be a little easier. Both AOs on the current homework on enemy AI are much easier than most application objectives you've seen so far, which is consistent with what I've been saying. I like to ease off on the end of this, towards the end of the semester. AO2's got its challenges. AO2 on enemy AI, it's one of those things where either you fully understand the content that I've been presenting in lecture and you understand the structure of the handout code that I gave you, and then you can do it like, I don't know, minutes maybe. But any misunderstanding anywhere along the way is going to turn into hours of studying. So that's one where if you're all studied up and everything makes sense to you, you can just walk into it, and the actual coding itself isn't too bad. If you're comfortable with trees, first-order functions, inheritance, polymorphism, like you got to be familiar with a lot of stuff in the course. If you are, easy. If anything's lacking at all, it's one of those things that can seem nearly impossible. It's one of those ones you'll stare at and say, I don't even know what the hell he's asking me to do. But once you understand what I'm asking you to do, it's not that hard. AO1 on enemy AI is, I think it's free. I think that one everyone should be getting. And the only way you're not getting that is if you need an extension on the, past the checkpoint to get the LTs done. If you got the lecture test done by the checkpoint, you better be getting AO1 as well. Get your AO1 on the next homework. Yeah. How are they broken up? So for the final, the structure of the final is I'm going to give you multiple app feature sets. I'm going to explain an app from a user perspective. Let me say that. I'm going to explain an app from a user perspective. Like, I want a banking app where I can deposit money, withdraw money, transfer money between accounts, etc. So I'm going to give you a list of those and say, here are the apps. I'm thinking like 4 of them. I'll give you a list of 4. You'll get to choose any 2, and for each one, explain how you would design software to build that app. And I'll have separate questions for each of the 4 learning objectives. So for LO1, I'm going to ask you, how are you going to test this? Tell me one specific thing that you're going to, at least one, specific thing that you're going to test. For LO2, where are you going to use polymorphism and inheritance, or where could you use it? For LO3, where can you either use functional programming, recursion, etc., or concurrency? And for LO4, where would you use either a tree or a graph? I'm going to ban linked lists from that because we use linked lists all semester for everything. Where could you use either a tree or a graph? Even if that last one's a little bit contrived, just tell me some way that you could use a tree or a graph in there. If you satisfactorily answer all those for either one of those, that's an AO. If you do it for both, that's 2 AOs. So if you go into and it's designed like that partially, if you go into the final only needing 1 AO, just do 1 app and spend all of your time on that one, making sure that that one's solid, instead of splitting your time. Or if you want to do 2 anyway and just double your chances, that's fine too. But you get that decision of how you want to approach that final. Any specific higher CS courses you would recommend that are related to GA? Not necessarily the genetic algorithm, but the intro to AI, of course, machine learning, anything in the AI machine learning category, anything that counts for any one of those courses. It's hard to recommend one over the other. Genetic algorithm itself, you're not really going to see. Genetic algorithm it's a glorified guess and check algorithm. Which I like because it's palatable enough to introduce in a 116 class. Because if I pull in like neural network, well, I do kind of pull in neural networks just because it's an AO2. But if I pull in neural networks and force you to do that or anything more sophisticated, linear classifiers or whatever, it's just not appropriate for a 116 course. So you're not going to. But to the other side of that, let's me thought a second. Genetic algorithm is basically a glorified guess and check program. It's a hill climbing algorithm, but it has a lot of randomness. which is to say that it's pretty bad. Like, it's not something you're actually going to use in industry. No companies, Google's not sitting there on a pile of genetic algorithms that it's using. It's using much more sophisticated models that take a lot of linear algebra, a lot of calculus to be able to do that. So take courses. I would start with Intro to AI and go into machine learning. Machine learning is going to focus on classifiers, which take feature vectors, take the problem, something that you want to classify, convert it into a feature vector, throw that into the algorithm, and see what comes out the other end, and it'll classify it. For example, one of the assignments that I think they're still running this assignment, you get a data set of handwritten digits, 0 through 9, and given the image, extract a feature vector for the image, throw it into your AI, and have it classify which of those 10 digits it is. Is one of the things you do in that. And in general, that's how a lot of AI works. A lot of it's classifiers. Here's a thing. Tell me something about this thing. Like, what is it? And once you get there, then there's all kinds of cool AI stuff you can do once you have accurate classifiers. But Intro to AI and machine learning would be the first places I would look. Then there's like computer vision and some others. We have a lot of AI courses. But you're not going to see GA again because just give up, Jesse 2021. I didn't say that. I said cut your losses. Yeah, and you can't. Don't even try. It's not. And I know you're joking, but let me rephrase it because I believe you can do anything that you put your mind to. I'm saying if you haven't put your mind to it until the day it's due, like you didn't put your mind to it already. Like cut your losses at that point. If it was a week ago, I'd tell everybody, you can do AO2 if you really want to, but you got to be motivated for it. If you don't care about machine learning and you don't care about that kind of stuff, you're not going to be motivated to see it all the way through. I think systems programming would be useful for a math student. It all depends on what you want to do. I mean, I'm biased. I think any kind of programming or any computer science stuff will help you. The world runs on computers these days. Anything that gives you a better understanding of what the hell computers actually do is going to benefit you. And systems shows you that low-level stuff of how computers work. If you're going into strictly a math field without programming as a component to that, which is pretty hard to find these days, then maybe it's not so helpful. But if you're going into something with any programming involved, which is, a lot of fields, like you just end up programming these days because then it'll help you out. Like most mathematicians, even in your math classes, you're using either Python or MATLAB to build models and visualize data and things like that. Getting an understanding of the low-level inner workings of a computer won't help you directly, I wouldn't say, but it will help you just in your understanding of what's happening underneath the hood. But at no point unlikely in your career, even as a computer scientist, maybe, arguably, debatably, depending on exactly what you're doing, will you take the systems programming knowledge directly and say, I really need to do this exact thing. Like I need to manage my own memory, for example, is one big thing you'll do in 220. You won't have to do that, but having an understanding of what happens underneath the hood is helpful. Test 4 for AO1. The hidden test 2. So there's 4 tests for AO1. I do have some leniency on this. I'm guessing you guys. There is some leniency on this. You have to get 3 out of the 4, and it'll say, this is good enough. It'll give my passive aggressive, like, you didn't complete all my tests, but whatever, I'll let you do it. What?
Like he said, it's like, it's good enough, if you suck. You don't know
So you have, I see. So you have 3, you have credit, you want that 4th one. I'll just spoil what my hidden test cases are. So for my hidden test cases, I have a separate object and class with the same structure as song and playlist, where I have an incubator and a cost function. For the hidden test case 1, it's the simplest that I could make it. It's just a double. So the class has one double. The incubator takes a list of length 1, a set of genes of length 1, and that double is the value. That's the hidden double. And then the cost function, given another double, what's the magnitude of the absolute value of the difference? How far away is it from that double? It's basically like a number guessing game. I'm thinking of this number, guess what it is. And then the genetic algorithm has to narrow down to that double. For hidden test case 2, it's got 2 doubles. You got to guess both of them simultaneously with the genes of length 2. So if you write those classes, you can simulate exactly what I'm testing and test it locally. Does that make sense? Any follow-up on that? 3 and 4. So the hidden test case 1 and hidden test case 2, which are tests 3 and 4. The first 2 are exactly what they say. Songs. I take the whole songs file and make sure you get at least close, at least like the top 5 songs. I think I'm a little lenient on that. And then playlists, as long as the cost of your playlist is within some margin of error of the optimal playlist, given the entire song and some map that I created for the user ratings, then you're good. Those ones are exactly what they say. There's not pulling any punches there. The hidden test cases, they're as simple as I can get. The simplest single gene and the simplest 2 genes. Just straight up doubles that are exactly the genes. And then for the tests, I generate a random number from, I think, negative 100 to 100, and see if your genetic algorithm can guess it. Within like 2 decimal places, I think. You have to get pretty accurate on those ones. Yeah, no problem. I think I missed something in there. I don't want to just have you stare at me staring at my phone. If there's something I missed, if you can repost it. There were other questions, but the TAs have them. Like tail recursion is when the recursive call is the last expression that's evaluated in that method, and then the compiler can, or the interpreter can crunch down all those stack frames. So the new stack frames are replacing the old ones instead of being added on top of them. So it prevents stack overflows. It's really good for memory management. Not by a significant amount. It wouldn't change the speed of the program. But the most important thing is it's not going to overflow the stack. So if your genetic algorithm is not tail recursive and you want 2,000 generations, you might overflow the stack. But if you're tail recursive, you could have 1,000,000 generations and you're good to go. I mean, it'd be slow, so you wouldn't be, you'd be timing out, you'd be taking forever. But it wouldn't overflow the stack. It wouldn't crash. And I'm sure you'll see some optimization just because there is a lot of memory saved. But as to like how much more efficient it would be, I'd imagine not too much. I haven't tested that myself. But it's generally better. Whenever you're writing recursion, like I don't care so much in this class, but whenever you're writing recursion for the future, in terms of grading anyway, in the future out there in the industry, whenever you're writing recursion, try to write tail recursive. It's just got a lot of benefits. At least marginally efficient, and just not crashing is the most important thing. You get your Really?
Yeah. I just thought that was interesting. Or
That is
maybe
interesting.
I'm an idiot and I read it wrong, but it wouldn't let me do tail recursion for that.
Wonder if we could test that. No, it let me. You might have something else in your. So if we, and by the way, if you add the tail rec annotation, oh, it's actually not yelling at me. This should give us an error. Let me try running it. We're just rerunning it. If you have the tail rec annotation, yeah, okay, there's my error. If you have the tail rec annotation, it'll give you an error if it's not actually tail recursive. That's the benefit of adding that annotation. Then it'll yell at you. And you can also look at this squiggle. Like this is a recursive algorithm, and that's a tail recursive algorithm. So you can look at that squiggle, it'll tell you too. So there might be something else in your algorithm, in your method, that's preventing from being tail recursive. Like maybe it's, like if this is else if, oh, I need a condition. Oh, because there's no recursive call. Yeah, that would work too. Yeah, but that should be tail recursive. But yeah, I'd be interested to see that one because that should work. That should work. All right, let's do this. I'd be remiss if we didn't do at least one tree example today. So let's go through this tree example. I'm just going to set the breakpoint for the first line of main. Just step through the debugger and see what happens. See what's going on in this tree example. So I'm going to step into my method. We have the main stack frame and the stack frame for this method call on the stack. And let's just create a binary tree. You'll, like 98% probability that you're going to see code that looks very similar to this on your quiz. So being able to read this will be of benefit. So we're going to create a root node where the left and right child are both null. It's the first thing we're going to do. This goes into the constructor. It's going to set the three values, left, right, and value. Nothing else to do, so we get that tree, that binary tree node, and set that equal to the root. So we got a node at 801, value 5, left and right are null. And the way we're building these trees is by overwriting those left and right variables. So I'm going to say root.left, which is currently null, because we set it to null right here. We're going to set that equal to a new node. So we're manually creating new nodes and setting those equal to the child nodes of nodes that we've already created. So we're going to create a new node with the value 2. In the constructor, it looks like it's going to be at 803. And then set that equal to root.left. So root.left is now a node with value 2 and left right of null. So root left was null. Root.left, it's now at 803, that new node that we just created. So I want to make sure there's no confusion about what's going on with these. Then we're saying root.right. I'm going to step over this time because I don't need to go into the constructor call again. I think we get that. Root.right equals a new node with 8. So now it's right is a new node. We got 805, 8, null, null. So we've replaced both of those nulls. Where we created the root, left and right were both null. We've replaced both of them. Root, left and right, not null anymore. They are referring to nodes. I've seen that before. I don't know if that's obvious or not or what, but I've seen that on quizzes before where they're like, oh, left and right from root are both null because, they're both null. They just look at this line, root, null, null. Of course they're null. No, we replaced them on the next two lines. And then we're going to do the same thing for those children. I'm going to skip over a bit here. Root.left, we're going to take the root.left, which was null, and we're going to replace that with a node that has value 3 and left, right of null. So we can start seeing the structure of our tree. We have the root. It has a left and a right. The left's left and right. The right's left and right are both null. We haven't set those equal to anything. So we have a root of 5. Its left has a value of 2. And then to the left of that, a value of -3. And to the right of that, a value of 4. Which is the same tree that we built in the slides. It's the same tree. That's the one we're building in the code here. And if we keep going, we're going to see those right values being populated. The right tree we just built left and right, 7 and 14. In that tree. So that's the structure of a tree. That's how we're building the tree. One of the quiz questions could be, it's hard to do this without pen and paper. It's a lot easier when we used to do it there back in the day. Draw the tree. So we might have you doing some ASCII art. I don't know. Maybe I just don't like that question. Maybe I'll just say, actually we'll probably just say when in order traversal runs, what's the order in which they're printed to the screen, and then just imply that you knew the structure of the tree. So we're going to call in order traversal. I'm going to click. Oh, actually I want to do that slower. Let me start over. I mentioned this before, but it's worth mentioning multiple times. I'm going to step into, and the debugger is giving me an option here. Whenever you see this, it's asking, which method do you want to step into? It's frustrating. I don't like that it does this. I wish it just stepped into the first one that's executed, the next stack frame that's added to the stack. But this is what it does. It'll ask us to choose one of these two methods. And if we just click step into again, we don't know where we're going to go. Here we ended up in order traversal. That's where I want to go anyway. So I'm fine with that. But to make sure that we go where we want to go, To make sure we go where we want to go, I'm going to click on the one that we want. These kind of effectively turn into buttons. I can click on either of the highlighted methods. I'm going to click on in order traversal because that's where I want to go. I want to go into this method. Let's take a look at the recursion of in order traversal. And for this, the most interesting part are going to be the stack frames. For the quiz, if we give you a breakpoint in an in order traversal, the stack frames is the part that we really want to look at. That's the part that is interesting. That's the part that's important for you to know. So we called this a node, which is the root of the tree. If we go back to our main stack frame, we can look at not our main stack frame, our binary tree example. We can see the references that we got. The root is at 800 left and right, 939, 940. We can see all the references there. So back where we are, we have a node at 800. So we know we've got we don't know in this method, but we know from the debugger that we have the root of the tree right here. So we have the root of the tree, which we can verify. We can look at left and right and see that we have all of the values of the entire tree. We got this whole tree sitting here. We only have a reference to a single binary tree node, but it has references to the rest of the nodes, either directly or indirectly. And we have the function. This comes up a bit. The function is technically stored on the heap. We can see that with the at 936. But I'm not concerned with that for LO3. I never talked about it in class. I don't expect you to just know it out of nowhere. But it technically is an object on the heap. All right, so we're going to check, is node equal null? Nope. We have the root node here, in fact. So we're going to make a recursive call on the left node. So node.left at 939, which has references, other references to other nodes. We're going to make a recursive call on that left node. So now node is that at 398, or 939. We're going to make that recursive call here. Is it null? No. So we're going to make a recursive call on its left value, 942, which is going to be a leaf node, meaning that it doesn't have any children. So we're a few steps down in the recursion. We still have this recursive call with the root. We have this recursive call with the root's left child. And we're about to add another recursive call with this node's left child. So we're going to have 3 recursive calls on the stack right now. This one, the node is going to be null. Oh, no, I'm off by 1. Then we're going to go one more step. This one, the node is going to be null. Since the node is null, we just made a recursive call on a left child, which was null. We're just going to skip this method. We hit the base case, which effectively does nothing. That stack frame returned And on this stack frame, where the node is this -3, we just went to the left, null. Now we're going to visit the value, which prints -3 to the screen. We look at the console, we should get -3. Print -3 to the screen, and then make the recursive call on the right node. The important part here is the stack. How much, we still have these values on the stack. I just clicked through them. Let's not do it again. But we're going to make this recursive call on right, which is null. Null, do nothing. And then, oops, it returned. Right, do nothing. So we're back at the node with 2. We just visited left. We did everything over here we needed to do. We just visited 2. That should be in our console. And now we're making the recursive call on the right of this tree. We're just going to call recursive call null. We see the stack frame go on. Stack frame returns. Print. Make the recursive call. And then return back up to the root node. And then after that, we're going to print the root node to the screen. And then do the whole same thing over on the right subtree. Go to the right, make recursive calls, make recursive calls. But the recursion is what's tracking the ordering here. We're making the recursive, we're visiting the node right in between the 2 recursive calls. So we're able to get the order that we want, in order traversal in this case. And the stack frames are maintaining all that information for us. Should I go over Scala doc? I mean, I could, I guess, in 3 seconds here. So if you do comments like this, it'll end up generating Scala docs for you. It's a way of documenting what your methods do in classes. That's as far as I'm going to go because it's 2:40 anyway. So have a great weekend, I guess. Anybody have any last questions? Have a great weekend. See everyone Monday.